Good morning, grade 12s. Welcome back. It is Tuesday morning, June the 2nd, and hope things are going well for you. I do want to start off with a verse of the day today, and again, as we're working through this planetary mechanics unit, I think my verses of the day are going to have to do with somehow, some way, stars or the sun or things like that within the universe. And so today's verse of the day comes from Genesis chapter 1. And I'm going to read for you verses 14 through 18, where it says, "And God said, let there be lights in the vault of the sky to separate the day from the night, and let them serve as signs to mark sacred times and days and years. And let them be lights in the vault of the sky to give light on the earth. And it was so. God made two great lights, the greater light to govern the day, and the lesser light to govern the night. He also made the stars. God set them in the vault of the sky to give light on the earth, to govern the day and the night, and to separate light from darkness. And God saw that it was good." Just for a moment, I just want to focus on the one sentence in there. It's a short sentence, and we tend to gloss right over it, but it is an important sentence. The sentence is, "He also made the stars." Right? Simple sentence, but profound in the sense that when we look at the universe and we see the number of stars out there, it is estimated that there are 1 billion trillion stars in our observable universe. And so when you think about that number, you can't even imagine that number. But again, we can look up at the skies and we can see just the portion of sky that we can see. The stars are uncountable. We could not count them. And so that estimate of 1 billion trillion stars in our universe is an immense number. And it is summed up here in the sentence, "He also made the stars." Profound. Awesome is what that is. All right, yesterday you looked at some of the history, you listened to some of the history, you saw some of the ways the model of our solar system changed through time. And again, as time has progressed and technology has progressed, we have been able to see further and further into the universe and come up with better and better models of what our universe would look like. Today we want to focus a little bit on Kepler's law. We talked about them in the video yesterday. He had 3 laws, and this is his third law. The third law is the one where the math comes into play. The third law said that the square of the period of revolution was proportional to the cube of the object's mean distance from the object it's rotating around. Most cases it's the sun, but Earth has satellites surrounding it. And so the formula, the proportion, and the formula work for those as well. So let's talk about it a little bit. So when we look at that, it says that the cube of the radius of revolution is proportional to the square of the period of revolution. To change a proportion to an equation, we need a constant. And so that's written this way. R cubed, the radius, divided by the period squared equals k. K is for Kepler's constant. Now, for objects in our solar system revolving around the sun, Kepler's constant is 3.35 times 10 to the 18 meters cubed per second squared. All right, so that is planets revolving around the sun in our solar system. Not always the case. So in today's assignment, you're actually going to find what is Kepler's constant for a satellite of Earth. In fact, you're going to do it for the moon. It says satellite, and then there's a little note that says, remember, the moon is a satellite of the Earth. And you'll be able to find Kepler's constant. Again, for that, you'll use the moon's period of revolution, its radius of revolution, and its period of revolution, and be able to find what k is for the moon as it revolves around Earth. So, knowing that Kepler's constant is constant for planets in our solar system, it allows us to write an equation like this. If we're looking at 2 different objects, a planet A and a planet B, we can set it up so that it is the radiuses cubed over equaling the periods cubed. There's a ratio there because they would both equal to k. And so we can make both sides of that equal to each other, and we can get this equation here. And you might get a question here or there where you'll use this equation if you have 2 planets or 2 objects that are revolving around something else. You can use this formula. We're going to do a quick example on the other board, and that will bring us to the end of today's lesson. All right, so here's our example. This should be a fairly straightforward one. We have an asteroid that has a period of 8.1 times 10 to the 7 seconds. What does this mean, radius of orbit about the sun? All right, so the first thing we're going to recognize is that asteroids are in our solar system. Okay, there's an asteroid belt between Mars and Jupiter, and as revolving asteroids in that belt revolve around the sun like all the planets. What that means is Kepler's constant is the same. It is that 3.35 times 10 to the 18 meters cubed per second squared. All right, so we're going to set up our formula. R cubed over t squared equals k. I'm going to rearrange it to solve for r. So solving for r, I get the cube root of k times t squared. We plug in our numbers. It's the cube root of Kepler's constant times the period. Plug that into your calculator, and you will get the answer of 2.8 times 10 to the 11 meters. All right, so straightforward. This is about as hard as the questions get, unless I give you questions with two planets, where you have to combine them. But again, it's not that bad. And so what you're going to do now is you're going to find 3 questions on Connect and a handout, as well as I'm going to give you a chart of solar system data. As you may need, some of the masses, some of the radiuses, some of the periods of revolution, and those kinds of things. As we move further into this unit, those are some of the numbers you're going to need. So you'll find a chart of solar system data, and you will find 3 questions for your assignment to do for tomorrow. All right, have a great day, and we will see you tomorrow.